Hello ladies, it's Mr. Sullivan. Today we're going to be looking at lesson 4-3, Algebraic Proofs. Giving you the heads up, this is not a topic that is tested on the Regents. I can give it to you on a quiz, but it's not going to be on the Regents, but it's going to really help us with our proof writing since this is the first proof that we're going to learn. So today's learning target is I can construct an algebraic proof by solving an equation. So the reason why we're going to learn algebraic proofs first is because a lot of the reasons we're going to be using are going to pop up in the geometric proofs that we're going to eventually take part in. So algebraic steps with supporting reasons used to solve problems and form deductive arguments. That's what an algebraic proof is. You're basically putting into a chart every single step that you did in solving your equation. So the algebraic properties of equality and one oddball. So you're going to see here that we have a bunch of reasons that we can use for justifications in our proof. So we have addition. Let me make my highlighter a little thicker. We have addition, subtraction, multiplication, division, substitution, reflexive, symmetric, and distributive. This one right here is your oddball, the distributive property, because it doesn't really pop up in geometric proofs. It pops up in algebraic proofs, but not often with geometric proofs. Because when we look at geometric proofs, we look at segments, we look at angles, we look at our visual, and there just really is no distribution. You don't need to write down the addition property of equality or the subtraction property of equality. You can just write addition and subtraction and so forth. So the reason what makes this a little interesting or confusing with algebraic proofs is that when we say addition, we don't typically think of like addition as like whatever we have been. Remember, when you're actually adding or subtracting or multiplying or dividing to an equation, what you're doing is you're doing it to both sides. So like often you say, Mr., put 3 on both sides. But no, you need to say addition of 3 to both sides. But you don't have to say addition of 3, you can just say addition. You need to say division and so forth. So the addition property of equality, if A is equal to B, then A plus C equals B plus C. So that's your stuff. These are all, you can read them. But again, the ones that are above distribution are the ones that we're going to be using in our geometric proofs quite often. All right. So one of the things is what will be in every proof that you write? The statement of the original problem. So typically you're going to be given a given. You're always going to be given information. It sounds very redundant to say given a given, but you will be given these things called givens that we know to be true. When we do our geometric proofs, you're typically going to be given a diagram, but you're going to have to mark it with the given information. You're going to have to label your diagram. And one thing I do require is that I need you to redraw those images. So when you're doing proofs, make sure they're done on a separate sheet of paper, and you mark them as you do the proof. A restatement of the given information in your proof. So even though it's given to you, it still needs to appear in your proof. Every single thing that you do has to appear in your proof. You also need complete reasons for each step in your proof. And last but not least, the final statement always will be your proof statement with a supporting reason. So here's a little taste of a proof. This one's a sort of abridged version. This one isn't 100% correct, but this is to get our mind in the motions of how to write a proof. So we're given this equation, 1/2 x plus 6 equals 10, and we want to prove x equals 8. Well, in the past, you would typically just solve this and say, Mr., x is equal to 8, I just solved it. But no, I want to see it in a proof form. So what we're going to do is I'm going to write 1/2 x plus 6 equals 10, and one thing I'd recommend is always solve your equation. So 1/2 x plus 6 equals 10. Well, the first thing you want to do is you want to subtract 6 from both sides. So I'm going to subtract 6, and I get 1/2 x is equal to 4, because 10 minus 6 is 4. And then another thing we do is we typically divide. So you can multiply this by 2, or you can divide by 1/2. So I divide both terms by 1/2, I get x to be equal to 8, which is exactly what I wanted to prove. But here's the issue. We want to put it into a proof. So whenever you put it into a proof, you're going to have statements and reasons. The statements are the steps to solving this algebraic proof. It's not always going to be algebraic. 99.9% of the time, it's going to be a geometric figure we're going to be looking at. So the first statement always is your given information. So if you look, 1 second. My first statement is 1/2 x plus 6 equals 10. If you look, that is given to us. So all we're going to write down is given. You don't have to write anything else. You just write given. Now, this proof skips some steps. When you go to our next page, you're going to see that I have every single step in there. But for this proof, we skipped a step. And we're going to go over that step on the next page. But I have to ask you, so how does this equation in step 2, or statement number 2, look different from our first statement? Well, if you look, I got rid of my 6. But how did I get rid of my 6? Well, I subtracted it from both sides. So my reason for why 1/2 x equals 4 would just be subtraction. And that's all you'd have to write. And now, if you look, I got x by itself. And I did that by dividing by 1/2 on both sides. So my final reason for why x is equal to 8 would be division. And that's it. So like for your classwork today, you're going to end up actually doing a whole algebraic proof by yourself. But the next 2 proofs, we actually are going to fill in the blanks together, and then we're going to do one totally together, where we have no statements and we have no reasons. So you've solved algebraic equations for years now. You solved them with me in Algebra 1, you solved them in 8th grade, you solved them in 7th grade, and you even solved them in 6th grade. So you've been doing them for years. We should know how to solve an equation by now. You've done many of these steps without thinking. I know some of you can solve an equation by not showing every single step, but here's the issue. You are in geometry. We need every single step shown because that's just the way geometry works. So what we're going to do is we're going to complete the following algebraic proofs using the algebraic properties of equality. If a step requires simplification by combining like terms, you can write simplify it, or you can just write combine like terms. I'm not going to be very picky with that. So in this question, we're given the equation 3x plus 12 equals 8x minus 18, and we want to prove x equals 6. Well, if you look, our first statement, this is a fill-in-the-blank algebraic proof because we have all of our statements written. We just need to write down our reasons. If you look, my first statement is always my given information. So I have 3x plus 12 equals 8x minus 18. That matches up to what I gave you. So I would just write down given. And that's all you would write for reason number 1. Now, for number 2, I wrote 3x is equal to 3x. That is the reflexive property of equality. The reason why we call it the reflexive property is because I have the same thing on both sides of my equal sign. So in this case, I have a 3x equals 3x. And whenever I can do that, I can just say the reflexive property. It's sort of like when you look in the mirror and you see your reflection. It's the exact same thing. So for this one, I would write down reflexive. You don't have to write down reflexive property. You can just write down reflexive, and I'm fine with that. And so is Miss Danielle. Step 3, I got 5x minus 12 equals 5x minus 18. Well, you sort of have to ask yourself, how did I change this equation to 12 equals 5x minus 18? Well, if you look, this part of my equation no longer has a 3x. It just has the 12. So I got rid of my 3x by subtracting 3x from both sides to get my 5x. So for my reason for number 3, I would just put subtraction. Now step 4, if you look, I have 18 equals 18. That's the exact same thing as step number 2, where I had 3x equals 3x. It's just 2 different terms. And I can say the reflexive property again. Number 5, I have 30 is equal to 5x. Well, if you look, my 5x stays the same. The only thing that changes is my minus 18. I got rid of it by moving it to the left-hand side of my equation. So if you look, how did I get from a 12 to a 30? Well, that means I'm going bigger. So whenever I'm getting bigger, it's addition. So I used addition on this example, or this step. Addition. Number 6, that's the exact same thing as number 4 and number 2. I used the reflexive property for 5 equals 5. And then last but not least, I got 6 equals x. So to get rid of my 5, I divided by 5 on both sides of my equation. So when I got 6 equals x, I did that by division. So I can say step number 7 is division. But here's the issue. We know 6 equals x and x equals 6 are the exact same thing. But I wanted to prove x equals 6. So I actually need to make sure that my final statement matches up with that x equals 6. I can't have 6 equals x as my final statement. I would actually take off a point. So the way we do that is we use the symmetric property, where you basically just are able to flip it around. And if you look, if a equals b, then b equals a. That's the exact same thing as saying 6 equals x, becoming x equals 6. So my reason for number 8 would be symmetric. Now let's go on to our next example. Given c equals 7.25s plus 15.95a, given a equals 6 and c equals 298.70, prove that s is equal to 28. So just giving you the heads up, not every time you're going to be given the statements and reasons. This is just like a fill in the blank sort of day because I want to get you familiarized with how the proofs are written. One of the things you need to make sure is that your proof takes up the width of the page, so it's not going to be just like a portion of your page, it's going to be the width of your page. So you're going to have a nice little table that you're going to write in every single time that says statements and reasons. Statements on the top left, reasons on the top right. Remember, your first statement is always your givens, and if you look, my givens are all right here. So my first reason is going to be given. Number 2, if you look, 2.9870 equals 7.25s plus 15.95 times 6. If you look, what we did right here was we made some substitutions. I put my 298.70 where c was, and I put my a value, I put my 6 where a is. So all I would write is substitution, because we're plugging it in. So if you think about it, you can't write plug in because that doesn't sound very fancy. You want to sound like mathematicians. So you would say substitution. Step 3. If you look, I actually finished the 15.95 times 6. Here's the issue. You might think that it says multiplication. You can't write multiplication, sadly. You actually can't write that down because when you're doing multiplication, you would be multiplying on both sides of your equation. And if you look, I'm not multiplying this side of my equation by 6. You're only doing it to that one side. So when we do this, we would just write simplification, simplifying. So you're simplifying because you're doing the 15.95 times 6, which will give you your 95.7. Now, step 4, when I said 95.7 equals 95.7, that's the exact same thing on both sides. So that means I'm dealing with a reflexive. Number 5, I have 203 equals 7.25s. Well, if you look, my equation, I started with a 298.70, and I had my 95.7. It was positive, and I'm getting now a smaller result. I went from 298.70 to 203. So I got rid of my 95.7 by subtracting. So I can just write subtraction, because I am subtracting from both sides of my equation. Number 6, that's a reflexive again, because that lines up with the exact same thing in the other examples. And then last but not least, I had to get rid of that 7.25 somehow, so we divided to get 28 equals s. So this would be a division reason. But if you look, I didn't want to prove 28 was equal to s. I wanted to prove s was equal to 28. So now that I'm doing a flip, I would say symmetric property for reason number 8. And that's it. Now let's do this proof together. Given 17 equals 3k plus 5, prove k is equal to 4. So the first thing I would do is I would actually write out my given. So in this example, number 1, I would write down 17 equals 3k plus 5. And my reason would be given. And you see how I'm numbering them? Make sure you number your statements and your reasons. Make sure they're next to each other because we want to make sure they're lined up. They're sort of like partners with each other. So what I would do is, since we don't have our statements already filled in, I would actually solve this equation. So let's solve this. So we have 17 equals 3k plus 5. I want to solve for k. So I'm going to subtract from my 5 from both sides of my equation. And I got 17, no, sorry, not 17. 17 minus 5 is 12, and that's equal to 3k. I now need to divide both sides by 3 to get k by itself. My 3's cancel, and I get k is equal to 4, or 4 is equal to k. So I solved it. Now we're going to put all those steps into a proof. So if you look, the first thing I did was right here, I subtracted 5. But before doing that, I need to say that 5 is equal to 5. So number 2, 5 equals 5, and that would be a good old reflexive, because we need to show every single step, and we need this step to appear in our proof. So our reasoning would be reflexive. Number 3, after I did my reflexive, I ended up getting 12 equals 3k. And I did that by subtracting by 5 on both sides. So I did that by subtraction. So reason number 3 would be subtraction. Then in step 4, I need this 3 to make an appearance. So I can say 3 equals 3. And that's going to be a good old reflexive. And then I got 4 equals k. And I did that by getting rid of my 3 by using division. But here's the issue. I want to prove k is equal to 4, not 4 is equal to k. So if you notice, there is a flip here. So when I do my flip, that's an example of symmetric property. So number 6, k equals 4, and the reason is symmetric. So remember, you're not going to be tested on these. I may give you an error analysis on a quiz, but I'm not going to make you do a full-out algebraic proof on a quiz or a test. We will be learning some baby proofs this unit. So basically like, oh, when I say altitude, what can you conclude and all that stuff. And then we're going to go back into some algebra stuff related to geometry. So we're going to look at some triangle stuff, and then we're going to like interweave some proofs in each of our units. All right. If you have any questions, email myself or Miss Daniel. And remember, Miss Daniel holds extra help every Monday, Wednesday, and Friday during second period. Ladies, have an amazing day.